This section is titled Exponential Functions. An exponential function is a function where a number, called a base, is raised to a variable. We have f of x equals b to the x. Notice b is the number, or constant, and x is the exponent, which is the variable. I have some qualifiers here. B has to be greater than 0 in order for this function to be an exponential function, and b has to be not equal to 1. Often students get the polynomial functions that we've been dealing with in the past confused with the exponential functions. So I want to make sure that you understand the difference by showing you several examples of exponential functions and non-examples of exponential functions. The first example of an exponential function we'll talk about is f of x equals 2 to the x. Notice 2 is my number or constant, and x in the exponent is my variable. Students often get this confused with f of x equals x squared. X squared is not an exponential function because the x variable is in the base and the 2 constant is in the exponent. This is exactly backwards. These are not the ones we'll be studying with right now. X squared we've actually already covered is a quadratic example, but we are not talking about quadratics today. We're talking about exponentials, or 2 to the x. Another example would be 1/2 to the x. Some students think that 1/2 to the x shouldn't belong, but 1/2 is a constant. It is greater than 0 and it's not equal to 1, so therefore this is an exponential function. One more example, f of x equals 10 to the 3x minus 1. This is a little bit more complicated example, although we still have a base that is a constant. We have a variable x in the exponent. We do have a few more other things, but this is still an exponential function because b is greater than 0 and not equal to 1. My x is in the exponent. A couple of more non-examples for you. Some students often confuse this one for an exponential function, 1 to the x. They'll say, oh look, 1 is a number. This is a constant in the base, and x is a variable, and that's in the exponent. But this one does not qualify as an exponential function because of the property where b cannot be equal 1. This is a kind of a boring function because if you plug any number into the exponent, 1 to the any number is 1. 1 to the 1 is 1, 1 to the 2 is 1, 1 to the 15 is 1. It's a very boring function and does not classify as an exponential function. It doesn't have the same properties, so we don't classify it as an exponential function. The last one is x to the x. We do have an x in the exponent, but my base is not a number or a constant, so therefore this is not an example of an exponential function. Before we start graphing the exponential functions, I want you to remember some properties from intermediate algebra that we'll be using heavily in this section. Any number raised to the 0 power is always 1. 2 to the 0 is 1, 15 to the 0 is 1, 1 to the 0 is always 1. Any number raised to the 1 is itself. For example, 2 to the 1 is 2, 5 to the 1 is 5, 7 to the 1 is 7. Any number raised to the negative 1, remember the negative in the exponent, that makes the base move to the denominator, and then we have a place holding 1 in the numerator. So x to the negative 1 equals 1 over x. Similarly, a over b to the negative 1, the a goes to the denominator because of the negative exponent, and the b is already in the denominator, so he actually goes to the numerator. These 4 properties we'll be using a lot in the next couple of sections, so I wanted to make you aware of those and remind you about the properties before we get too far into this. The next thing we're asked to do is to graph the following exponential functions. f of x equals 2 to the x is an exponential function because 2 is a number and x is the variable in the exponent. Similarly, f of x equals 1/2 to the x is also an exponential because 1/2 is a constant or a number, and x, the variable, is in the exponent. So for my first function, I'm just going to pick some values, -2 till 2, and plug in those values. 2 to the -2. The negative in the exponent tells me that the base is going to move to the denominator, so I have 1 over 2 to the 2, which is 4. 2 to the -1 tells me that the base goes in the denominator, 1 over 2 to the 1, which is just 1/2. 2 to the 0, well, anything raised to the 0 power is 1. 2 to the 1, anything to the 1 power is always itself. And 2 to the 2, well, that's just 4. Let's plot what we have so far. -2, a fourth, -1, a half, 0, 1, 1, 2, and 2, 4. Notice we have a little bit of a pattern here. The first f of x value we have is a fourth. The next one is a half. The next one is 1, and 2, and 4. There is a pattern here in the f of x values. It looks like it's doubling every time. 1/4 doubled is 1/2. 1/2 doubled is 1. 1 doubled is 2. 2 doubled is 4. So I'm going to guess that my next value would be 3. Let's check it. Is 2 to 3 equal 8? Yeah, it does. So I can go ahead and add that here. Similarly, if I go backwards, half of 8 is 4, half of 4 is 2, half of 2 is 1. Half of 1 is a half of a fourth is a half. So I'm going to guess that my next one is going to be 1/8. Let's try it. Is 2 to the -3 equal an 1/8? Yeah, it certainly does. So this keeps going. Half of an 1/8 is a 16th. Half of a 16th is a 32nd. Half of a 32nd is 1/64. Notice that I'm getting very, very, very small here, very, very close to the x-axis. If I keep taking halves and halves and halves of a value, am I ever going to reach 0 if I'm only taking half of it? And the answer is no. What that tells us is we have a horizontal asymptote, and the horizontal asymptote is going to be at the x-axis. So I'm going to make a little line right under here, making it a little low just so you can see it. But the x-axis is my horizontal asymptote. Let's try this again with f of x equals 1/2 to the x. I'm going to start with my same 5 values. 1/2 to the -2. Well, the negative in my exponent tells me that my fraction inverts. So 1/2 inverted to 2. 2 squared is 4. 1/2 to the -1 again tells me that it inverts to 2 over 1, or just 2. 1/2 to the 0, well, that's always 1. 1/2 to the 1 is a half, and 1/2 to the 2 is a fourth. Let's plot what we have so far. -2, 4, -1, 2, 0, 1, 1, a half, 2, a fourth. Notice that when I start for my negative x values and move to my positive x values, my f of x values are halving. Half of 4 is 2, half of 2 is 1, half of 1 is a half, half of a half is a fourth, half of a fourth is an eighth. Let's see if that actually works. If I plug in 3, 1/2 cubed, is that 1/8? Yeah, it is. And if I keep going, I'll get a 16th, 1/32nd, 1/64th, and so on and so forth. Notice that if I keep taking half and half and half and half of very small things, I'm never going to get to 0. Going the other direction, I'm doubling. A half times 2 is 1, times 2 is 2, times 2 is 4, times 2 is 8. I think the next one should be an 8. 1/2 to the -3 is positive 8. So my pattern holds. I can sketch my graph. We already talked about how if you taking half of a very small number, you're never going to reach it, which tells me I have another asymptote here on the x-axis. There's a lot of similarities between this blue function and this red function. The blue function is increasing from left to right, whereas the red function is decreasing from left to right, although my asymptotes are the same in both. My blue function is called a growth curve. It's called a growth curve because it's increasing from left to right. Another way we know it's a growth curve is because my base 2 is greater than 1. Whenever your base is greater than 1, you have a growth curve. The red function is an example of a decay curve. And the reason it's a decay curve is because it's decreasing from left to right. Notice that my base 1/2 is less than 1 but greater than 0. Whenever your base is less than 1 but greater than 0, you'll have a decay curve, meaning it's decreasing from left to right. Let's take a look at some of the similarities that we have in each of these graphs by finding some properties. My domain for the blue graph is -infinity till positive infinity because there is no value for x that I cannot plug in to get some f of x value. There's no forbidden or excluded domain value, so we assume that the domain is all real numbers, which it is. My range, on the other hand, we cannot have any negative values. When I take 2 to the any number, I never get a negative value. So my range is all the positive values from 0 to infinity, although I'm not allowed to include 0, so I put in parentheses. My x-intercepts, well, I have no x-intercepts in this graph because I have a horizontal asymptote in this graph. Remember, our values keep getting half as close to 0, but it'll never ever reach 0. But I do have a y-intercept. My y-intercept is at 0, 1. And lastly, my asymptote is a horizontal asymptote, which we've talked about, at y equals 0, or just the x-axis. Let's take a look at the same 5 properties of the red function. My domain, my values for x, can be any real number. There is no excluded number from the domain that would make my function undefined. I can plug in any value for x and I can get out a f of x value. My range, on the other hand, I'm not allowed to have any negative range values, so I start at 0 until infinity, not including 0 because I have a horizontal asymptote at 0. Because I have a horizontal asymptote at the x-axis, that tells me that I don't have any x-intercepts. I do have one y-intercept at 0, 1. Notice that that's the same for both graphs. I have a point at 0, 1. And my horizontal asymptote is y equals 0, or just the x-axis. Take a look at these properties here. My domain is all reals for both functions. My range is all positive values from 0 to infinity. Neither function has an x-intercept. Both functions have the same y-intercept, 0, 1, and both have the same asymptote. So I want you to note that although my bases were different on both functions, f of x equals 2 to the x and f of x equals 1/2 to the x, the bases were different. Although all 5 of the properties were exactly the same. And that's going to happen every time you have a function f of x equals b to the x, where b is greater than 0 but not equal to 1. Your domain, your range, your x and y intercepts, and your asymptote will all be the same. As the above two functions. Your domain is always going to be all reals. Your range is always going to be from 0 to infinity. You will never have an x-intercept. Your y-intercept will be 0, 1, and your asymptote will always be the x-axis, or y equals 0. notice that this is before translations. We're going to be doing some transformations, shifting left, right, reflecting, compressing on the next video. But for all functions of the form f of x equals b to the x without transformations, all the properties will be the same, which is kind of nice. Now, when we did some transformations in past sections, we used some key points. Now in these, the key points can't necessarily be the same here because my blue function doesn't look like my red function. My blue function was a growth curve or increasing. My red function was a decay curve and was decreasing. So our key points will be slightly different every time, although we're still only going to be using a few key points. Let me highlight your key points on each of these. If we only focus on -1, 0, and 1, for the x values, we can get 3 y values or f of x values very simply. And these are going to be what we're calling our key points. So let's take a look at this parent function f of x equals b to the x. If I have this parent function f of x equals b to the x, I'm going to try to find some key points in order to graph it. And once I graph with my key points, then I can talk about my transformations. All exponential functions in basic form will have 3 points on their graph, and we are going to be looking at those 3 points where the x is -1, where the x is 0, and where the x is 1. Now if I just make a little t-chart here and plug in -1, 0, and 1 into b to the x, I have b to the -1, and using our properties we know that's 1 over b. b to the 0 is always 1, and b to the 1 is always itself b. So you can memorize these 3 points. You will always have 0, 1. At -1 you have 1 over b, and at +1 you have b. And all you have to do is plug in your b, and then you can get your 3 key points. Let's take a look and make sure that that worked on our past 2 problems. On f of x equals 2 to the x, my b was 2. So the 3 points that I should have are -1, 1 over b, which is 1 over 2. 0, 1 is always a point, and 1, +2. Were those my 3 key points? Well, yes, they were. Let's look at the red function. If I plug in -1, 0, and 1, when I plug in -1, I get 1 over a half. Well, 1 over a half is really just 2. 0, 1 is always the value. And 1, b, and my b is a half. So I have 1, a half. Are those the 3 key points? Well, yes, they were. So these 3 values, or points, are going to appear on all basic forms of an exponential function. On the next video, we'll talk about the rest of the transformations from the basic graph.